Okay, so welcome again to Micro One. As I told you in the summer, we're going to do again chapter 4 with additional proofs. This is a very important chapter, right? So it's important that we actually go twice over this. So we have one more student from IB, so welcome. And again, so you missed the summer, right? But there's the recordings of the class, so I hope you can see it, right? I basically it's a refresher. So we're gonna go through the main chapter that I did in the summer again, right? And so you're not missing really anything fundamental. But again, you can check the videos and you can check basically the chapters that we cover there, which are essentially chapter 1 and chapter 3. Okay. Okay. So welcome everyone again, and we're gonna go to this modified and updated version of Masculine Wisdom and Green chapter 1, which is about preference and choice. It's basically a chapter introducing the notion of revealed preference and then how to match it to the utility maximization. So again, as we're doing this online, if you have any trouble with audio, video, just let me know, right? Also, the way we interact is just open your microphone and tell me the question, right? So I'm not gonna be checking the raise your hand option in Zoom because we're just a small class, right? So just open the microphone and tell me, okay? That's the way we interact. Also, I'm not gonna be checking the chat in Zoom. However, if you have questions, you know, that you need to write after the class and so on, use Slack. Anything that is on the chat on Zoom, the moment I leave the session will be deleted, right? I'm not going to be checking the logs, so try to write, you know, written questions in a Slack, but you know, for the class, verbal questions, not written questions. Okay, so just let's interact. Okay, so again, let's go over this chapter. I'm going to emphasize more the proofs today. Other parts I'm going to go, you know, a little bit less detail on the motivation as we spend some time on the motivation on the summer. Remember that basically the objective of this chapter was to connect what is called the 3 languages of decision theory. So this chapter is about consumer decision theory, and we have 3 languages so far. So choices or choice correspondences, which is essentially what we imagine is the data we observe out of a menu of alternatives, or alternatively, a special case is a budget that you face as a consumer. You are going to pick a particular demand or a choice alternative, right? And this is what this description of as an input, a menu, as an output, a choice, is called a choice function or a choice correspondence. This is the primitive of our study, and this is the first thing we deal with. And this is the first object or language in decision theory. The second object is preference relations, right? We study them in chapter 1. We know what is a binary relation, and we use them to model consumer behavior. So a complete and transitive relation, right, is basically a description of how individuals or consumers rank alternatives according to what they like, right? And with these 2 properties, completeness, being able to compare everything, every single pair, you're able to know what is better, right? And transitivity, which is that you have 3 alternatives, A, B, and C, and you observe that A is better than B, B is better than C, you must conclude that A is better than C, right? So these 2 properties that we remember, completeness and transitivity, they are what is called rationality in terms of preferences. So this is the second language, and this basically is a way to model preferences, right? So economists model human behavior by using preferences, right? And the type of preference we use to model consumer behavior are complete and transitive, right? And we call that rationality. The third language is basically utility functions. These ones you are super acquainted with, right? This is the thing you see in micro, in undergrad, in master level. So you write down a utility, and what's a utility, right? It's basically a function that will map alternatives to a number, right? And this number is a real number. We can even be simpler. It's a number between 0 and 1, okay? And the higher the number, the better the alternative, right? That's the main idea. And what we studied before is basically that there is this link between utility functions and preferences, right? Whenever you describe taste and preferences using a utility function, you end up having already automatically completeness and transitivity, right? Because a utility function is able to rank any two alternatives, right? So you know which item has a higher utility than the other, any two items. So that will give you completeness. And of course, it will give you transitivity, because if you observe the utility number of three alternatives and you have that the utility number of the first alternative is higher than the utility number of the second alternative, and then you have that this utility number of the second is higher than the utility number of the third alternative, then, and from now on, I'm just going to say utility instead of utility number, you will conclude that the utility of the first is higher than the utility of the third item, right? So this is automatically from writing a utility. So a utility basically is a way to model preferences that already encodes completeness and transitivity. And why do we take the trouble of using these three languages? Because they are useful in different contexts. You can think of the first one as being basically data you get from a laboratory setup, from a survey. Basically, you can think of the first item as being data. You can think of the second item as being a model. And this model, basically 2 and 3, the preferences and utilities, are a way to model behavior. So they are a mathematical description of how people behave, okay? So this is not data, this is a model. Now, why do we have two ways of doing models, right? 2 and 3, preferences and utility functions. And the reason is basically that they have different pros and cons. So sometimes it's easier to describe human behavior using preferences. Sometimes it's easier to describe it using utility. One deeper reason why theorists have introduced the language of preference relations is basically because it allows us to go beyond what utility functions can do. Utility functions will force you to be complete and transitive, right? And this is the classical model that most economists use, and possibly you would use in your life. But basically the human behavior not always will be consistent with transitivity, right? And experimentally, with evidence, people have shown that transitivity is not the best assumption. Hence, we have to move beyond that. And a way to do that elegantly and still keeping a lot of what we do in the theory is by using preferences, right? So again, this is just kind of a first, soft motivation that I kind of went deeper in the summer. But this is the three items we're going to deal with in this chapter, right? And the objective of the chapter is to connect them. Okay, so let's start with item 1. So we start with a data set, right? So again, this is a bit awkward, right? Because you're younger than me. So when you hear data, you want to see numbers, right? So this is going to be an abstract description, right, of a data set. Right, so essentially, we're going to have a physical counterpart of this. We can collect it from experiments, but right now it's going to be a mathematical description of such a data. Okay, so in particular, the object of interest, as we study in the summer, and we are going to study again and again, at least for the first 2 weeks, is the choice correspondence. So a choice correspondence is basically a mapping from so remember that, let's go line by line. So X is a choice. Mathematically, it's just an abstract set. So physical counterexamples of this, as we were mentioning previously, it can be, for instance, a set of lotteries. So imagine you go and try to buy a lottery in Ontario, right? You have 3 options, right? Lotto Max, second option, third option, right? So your choices will be L1, L2, L3. X actually can be anything. Can be a collection of cars, right? Collection of airplanes that you want to buy, the next computer you want to buy, right? Headphones, yeah. So X can be anything, and this is, situation dependent. So X right now, mathematically, is an abstract set, okay? The only thing I'm requiring right now is that it's non-empty. Do you agree? So it's very simple. Now, once you have that, I have this notation, 2 to the power of X. So, I'm shortcutting a bit, but I'm explaining with words. 2 to the power of X is the power set, right? So the power set basically means the collection of all subsets of X, right? And then I'm gonna remove from this collection the empty set, Okay, so just remove the empty set. And now the choice correspondence is going to be this mapping that is going to take one element in the power set of X minus the empty set, map it to the same power set. So in other words, I have examples later on, but fundamentally the only restriction of this mapping is that the choice correspondence C applied to set A has to be a subset of A. So it can only map to something inside the menu. And this, is if you map it to an experiment, this is obvious, right? So if I run an experiment where I show you 3 lotteries, I will expect you to choose something from these 3 lotteries, right? You cannot choose something outside, okay? So you have to choose something inside the menu. Do you agree? That's the only restriction right now. There is nothing fancy about it. One thing that is important is that I'm assuming it is not empty, okay? This is important, right? So you always have to choose something. So if I run an experiment, the subject is forced to pick something from the menu, okay? So this is a decisive choice. You have to pick something, understood? So this is the 2 restrictions. It's not empty and it has to be something inside the menu, right? So, and as you notice, I'm using this word menu to refer to the input of this mapping, right? Because this set is understood in our setup as a menu of alternatives, right? And then from this menu, you choose an item. Agree? So that's basically it. Now, one important thing. In general, right, sometimes choices can get really, really complex. For instance, you can have a choice that is infinite. You may think this is crazy, but actually this happens all the time. Imagine that you're trying to invest, as I was, this is an example I used before. You're trying to make investment and you're trying to make a portfolio, right? So right now, you know that fractional trading is getting more popular. Basically, you can buy a fraction of a stock, right? And this fraction can actually be any fraction you want. It's in fact a point in the reals, right? So that means basically your set of alternatives is the real line, right? And imagine you, instead of having one stock, you have multiple stocks. So actually it's the Euclidean plane, right? That's an infinite choice. Now, so what is important is this. So imagine I'm an experimenter, and now I'm faced with the reality that I will never be able to run an experiment for all possible subsets of the real line, right? So it's just impossible. So hence, I'm gonna start thinking of something smaller. And this something smaller is gonna be called the collection of budgets or the collection of menus. And we're gonna denote it by the calligraphic beta, okay? So this is just a subset of the power set. So instead of just seeing all possible power set, all possible elements of the power set, all possible subsets, I'm gonna focus only on a subset of them. Okay, so that basically means that in real life, experiments will be limited. I won't be able to look at all of them, all possible menus, right? I'm just gonna be able to look at a smaller collection. And this smaller collection of menus is gonna be called calligraphic beta. Understood? Okay, great. So now, we're gonna call a choice structure a pair of a collection of budgets, right? And the choice.
Sorry, could I ask you a question?
Yes.
So this set of menus, calligraphic B,
beta.
Is it necessary finite?
It may not be finite. So okay. Right now it's super abstract. It can be anything, right? But it's an object of interest. So in some setups, in real life, if you're thinking just of an experiment, it's impossible really to have an infinite collection, right? But because we're theorizing, we may allow, for instance, to have the whole collection of linear budgets, right? If you imagine, the Euclidean space, a thing of 2 dimensions, and then a class of menus is our budget hyperplanes, right? So just these hyperplanes in the 2D space. Now, if you think of the collection of all budget lines, right? Basically, this is an infinite collection, right? However, is smaller than the power set, right? So that's, for instance, a collection that we will study, the collection of all linear budgets, which is infinite, right? Yet not the power set, okay? Because there may be non-linear budgets, okay?
Okay.
Good. So a choice structure is a pair of the collection of menus, right? The calligraphic B and the choice correspondence. So the important thing is when I denote this choice structure, you must know that I will only observe choices from the observed calligraphic beta. So nothing outside that. So you take the original choice correspondence and basically you observe it only on the calligraphic B. You don't observe it outside. Do you understand? So that's my assumption. That's called a choice structure. Now, this choice structure also, this is the language of Mascolel, but modernly we will also refer to this as a data set. Okay. So this is basically something I collect from an experiment, right? And then basically this is the observed data. Okay, so I observe menus that are inside the calligraphic B, sorry, I'm gonna say calligraphic B from now on. And then you observe choices from those menus, okay? And then one example of an important data set or that we're gonna study is basically a rich data set. So when X is finite, or actually it can be also infinite, but basically I'm assuming that the calligraphic B has all double tones and all triple tones, okay? All double tones and all triple tones. So that means that we say a data set is rich when the experimenter was able to gather all possible pairwise comparisons and all possible triple tone comparisons. So I'm running an experiment and I was able to get all the double tones and all triple tones as a menu. I call this data set rich. Okay, so this is just language now, a definition. Do you understand what is a rich data set? Okay, great, thank you. So example, right? Imagine I have a choice set of 3 lotteries. As I say, lotteries in Ontario, right? So Lotto Max #1, a second lottery, a third lottery. I'm gonna create an arbitrary calligraphic B that has only 2 menus. Calligraphic B now has L1, L2, right? And L1, L2, L3 as a second menu. So this experiment, I just got money to run 2 menus, right? So that's my experiment, L1, L2, and L1, L2, L3. And then what is a choice correspondence? Choice correspondence, remember that is only limit to the observed beta, calligraphic B. So from L1, L2, this is a complete creation out of my mind. So it doesn't have to be like this, but this is the data set I'm imagining. So this person chooses lottery 1 out of L1 and L2. And from L1, L2, L3, this person has as possible choices L2 and L3. And again, I want to emphasize this. This is a bit weird because usually we think as choice as being a single item, right? And in fact, when it's a single item out of a menu, we call that choice function. But in this level of theory, we allow choice to be not completely decisive. We can allow actually the consumer to tell me that he actually may choose L1 or L3. So a way to call this is basically the set of choosable items, right? For short, in our course, we just say is the choice, right? So, and the choice is a set, L2 and L3, right? Which sounds a bit weird. But again, I explained to you that I think the best way to understand this and map it to real life is if I am an experimenter and I run menu L1, 2, 3 many times, right, with the same subject. And in the first trial, the subject chooses L2. And then in the second trial, the subject chooses L3, okay? So then in this case, how would you encode this information? You will encode it in this choice correspondence that says this person has chosen both L2 and L3, right? And then, as I kept running this experiment, the subject never chose L3, okay? So the encoding of this information is basically what you see. And this is a choice correspondence, okay? So everyone understands this. I know it's a bit complex, but this is important. This is gonna be the object of our study. Hence, we have to understand it really, really well. Okay, so any questions here are welcome. Else I will keep going. Okay. So important,
Sorry,
yeah, go
just one
ahead.
question. Are we saying that, you know, the consumer is different between L2 and L3, or are we just saying that he doesn't, because he's chosen both above L1? So I just want to make sure that that's correct.
Yeah, so both interpretations are fine, Ahmad. So in fact, you know, choice correspondence, as you can see, is a mathematical object, right? A mathematical object can always model different real life situations. So I think, you know, a reasonable theorist can take both your interpretations and say, you know, this is an instance that can be described using a choice correspondence. One thing maybe is more informative if I tell you a counterexample, right? Something that cannot be captured by a choice correspondence. So I mentioned in the summer, but I would repeat it again, that an instance that is not captured by a choice correspondence, a counterexample of a choice correspondence, right, is a situation where the experimenter is measuring the frequency of choice of L2, L3 in repeated trials. So the experimenter runs the menu L2, L1, L2, L3 100 times, and then records the fraction of times the subject picks L2 and the fraction that chooses L3, right? And then it turns out that, for instance, this experiment delivers that 50% of the time the consumer picks L2 and 50% of the time the consumer chooses L3, okay? So that's a situation that cannot be captured by a choice correspondence, right? Because the choice correspondence is not rich enough, it's not descriptive enough to capture frequencies of choice. But basically, the only thing that the choice correspondence can do is tell you that at some point, right, L2 and L3 were chosen. It doesn't tell you it's 50-50, it doesn't tell you if L2 was chosen one time, right, and L3 was chosen 99% of the times. That information is not in the choice correspondence. Do you see? So in a way, is very rich. It tells you a lot of information, but also is not covering all possible situations. So I think it's a better way to describe what is allowed and what is not. But from the two things you told me, Ahmad, I think both things were allowed. Okay.
It's much clearer that way. Thank you for clarifying that.
Thanks. Okay, so now remember item 2, right? So we are done with item 1. So choice. Now, item 2 was preferences, right? So this is the model. So now, of course, any theory starts from a primitive, a data set, and then introduces a mathematical modeling or description of such data. So basically, this is the first time we're going to connect item 1 with item 2, choice correspondences with preferences, okay? So here, of course, all of you, and I hope also Ling Shao was able to check a little bit the material, but we need to know what is a preference relation, right? And a preference relation, as you remember, is a binary relation, right? That is able to basically describe rankings, okay? Now, having this object, right, we can describe basically what it means to be a rationalizable, choice correspondence. So we say a choice correspondence is rationalizable whenever the choice correspondence out of a menu A is equal to this set. So this set is basically described by all items inside menu A, such that item B is the top of the rank, or the weakly preferred to A for all alternatives A inside the menu. In other words, B is a maximizer of the ranking in the menu, right? So this is it, right? So when this happens, and this equality is basically equivalence in sets. So it means that this set here, you take any item here, it belongs to this set on the right-hand side. And if you take any item in the right-hand side, then it also is an element of the left-hand side set. Okay, so equivalence of set means that they are both the same set. Okay, so set in the left is just data, set on the right is a model, right? And this is the set of maximizers of a preference relation given a menu. Okay, and when this preference relation is complete and transitive, we say it's rational, right? So this is the definition of rationalizability, okay? So this is it. Now, one important thing I want to also highlight is that we also have to know that when C A is just a subset of C star, instead of being an equality, right? We say C is weakly rationalizable. So just as a secondary definition that we need, okay? This definition, we're gonna use it later on, but this is a definition that is important when we don't have all the power set, okay? And we still have a collection of menus that is smaller. So it's gonna come later. Okay, so let's go to preference relations now. Yeah,
One question. When we are claiming that the preferences are rational, are before or after the definition of rational is that the choice correspondent is rationalizable?
Yeah, so remember how this goes, right? Basically, I'm gonna tell you in words what it means to be rationalizable, right? So it basically means that a data set can be generated, right, by a preference relation. That's what I'm saying, basically. So an alternative way of saying it. So you start from the primitive, which is the data, and you're basically saying there is actually a model of behavior, which is a preference relation that is complete and transitive, that can generate the same data I observe, the same choices from the menus. Okay, so this is what it means to say that it's rationalizable. So a data set can be rationalizable or actually can fail to be rationalizable. So there are some data sets that there is no way it can be generated by a complete and transitive preference relation, right? So basically a data set can be, this is just an adjective to a data set. It can be rationalizable or it can fail to be rationalized, okay? If that's what you wanted to know. Okay. Okay, so again, just a refresher of the chapter 1. So this symbol, right, that in LaTeX is this is the succession equality, right? But this is the symbol in LaTeX. But this symbol, has become the symbol for preferences, right? And as is a kind of a wiggle curve greater than or equal to symbol, right? So this symbol, right, is the usual symbol we use. You can change the symbol, it doesn't matter, but this symbol we're going to use in this chapter as a binary relation, and we know this is a subset of a Cartesian product of x times x, and is an ordered pair. So you learned what is an ordered pair a long time ago, right? And we're just going to write it a little bit differently. And remember that basically we write that A is in relation, in this case, preferred to B, even only if A and B are an item of the ordered pair. So don't forget this, right? So sometimes in notation, we get lost because this looks like a greater than equal to, right? And we just kind of automatize it, but always remember that this is just an ordered pair, and we write it as a shortcut, right? That A is in relation with B in this way. And in this chapter, we're gonna say A is preferred to B, okay? But so remember of chapter 1, but this is just something to have it in mind. And then two things that are important we're gonna use in this chapter are the asymmetric part of a preference relation, which is this symbol, the strict part, right? Is defined as A is in the strict relation with B, even only if A is in relation with B, and the symbol not, right? Not B in relation with A. So in words, A is preferred to B, but B is not preferred to A. This gives me that A is strictly preferred to B. Do you understand, right? And now we do something analogous to the symmetric part, which is the indifference relation. We say A is indifferent to B, even only if A is in relation with B and B is in relation with A at the same time, right? Which means they are indifferent, okay? Great, so remember these two symbols. Here there was a proposition from Mascolel that is good to practice proofs. I ask you to try to work on it, right? I'm going to skip it again this time. This is a useful thing to have, and basically tells you some properties of the relations, but it's really a practice proposition, right? That you can use to use your proof techniques and proof skills. Yeah, what is important from this basically is saying that the strict part of the preference relation that is rational will have some nice properties we study in chapter 1, namely that is irreflexive and transitive. What it means irreflexive is, of course, if it's a strict preference, you cannot have that A is strictly preferred to B and at the same time that B is strictly preferred to A, right? That's impossible, right? So that's basically being irreflexive. And transitive, you know what is transitivity. The transitivity from the original preference relation is inherited by the strict part, right? Obviously, if the transitivity statement that A is strictly preferred to B and B is strictly preferred to A, it will imply that A is strictly preferred to C. That's obvious, so that's inherent. And the indifference curve, we know this is what's called an equivalence relation. It has 3 properties: reflexive, transitivity, and symmetric, right? And you can go to chapter 1, but basically these are properties that are what makes an equivalence relation and indifference relation. And finally, this more subtle property that if you combine strict relations with weak relations, applying transitivity, you will essentially apply the stronger part, right? So that X is strictly preferred to Y and Y is weakly preferred to Z, you will conclude that X is strictly preferred to Z. And you please use it for proving techniques, but it's not very deep, so I'm going to skip the proof. Again, I mentioned this in the summer. Here I'm going to go lighter on this because I want to focus on the proofs. Mascolel has a small section where he and the co-authors discuss some issues with transitivity, right? And it's a little bit awkward in the Mascolel chapter because they kind of never go deeper into it, right? But what you have to have in mind is that even if we study the transitive and complete model, which we call rational, it's not the final word, right? It's not like the Newtonian physics or if you want relativity. So it's not the final word on behavior. It's not a fully validated model. Some people may behave rationally under some circumstances, right? But not everyone. And there's a lot of evidence that transitivity essentially can fail. And so you have to be aware that why we study this, because it's a good benchmark model that give us the techniques and the main ideas of how we do econ and consumer choice, such that when you can, and you need to expand the transitivity model to allow for more behaviors, you already know kind of a template of how to deal with data and behavior, right? And this is common from all sciences, right? So I always say this, and this is something that my own professor, Roberto Serrano, told me when I was studying this long time ago. And he told me, this class, Micro 1, you can think of it as physics without frictions, right? So forget about frictions, right? You are studying consumer in a vacuum, right? And then basically you can imagine that under a situation where a consumer doesn't have, has unlimited bandwidth, perfect attention, right? The stakes are high such that what you're choosing matters and you're fully committed to make the best choice. I think there is evidence that people actually try to behave consistently with completeness and transitivity, right? And so we're going to study this model under this perfect ideal choice situation. But in real life, of course, people are distracted. I may be worried, something happened to me. I may be low on sugar, right? And then my mind is not working properly. I'm lacking coffee, right? So we're academics. We need coffee, right? At least some of us. So all of that can affect the quality of your choice, right? So you can imagine that they start in this situation. Sometimes, your brain gets enticed by some property of a choice situation, and then you get distracted in a particular way, which is a lot of framing what is a lot of behavioral economists study. So again, I mentioned other examples here, the Condorcet paradox. You can read it if you don't remember. I read it in the summer, but remember that this is kind of a mea culpa of Mascolel saying, By the way, we're studying this seriously, but remember, it's not the final word, right? So it's not going to be a perfect description of behavior. Mainly what may fail is transitivity. But remember, this is kind of a core model, then you can augment and try to describe actual behavior in situations where there are frictions, so real life. Okay, so I'm going to skip this part. And the important thing that is going to link now preferences, relations, and utility functions, right, is a little theorem that we proved in the summer. That is that you can move back and forth preferences that are complete and transitive and a utility function. So here, you know, this theorem is from the summer, so I'm not going to be able to go deeper into the proof. But what I'm saying basically is that a preference relation can be represented by a utility function only if it is rational, right? So if and only if it is rational, when X is finite. And in particular, right, remember that the main idea here is that you can move back and forth between a preference relation that is complete and transitive and the use of a utility function. Now, with this in hand, right, we have our main connections, and we're going to dig deeper into results, right? So now, the main really objective of this class is not the utility representation theorem that we're going to do later on in a better situation with deeper details. Is rather the introduction of a key concept in econ and modern econ. And this is the concept of revealed preference relation, okay? So revealed preference in general, the concept of revealed preferences. And here, you know, is where economists differ from other social science. And, you know, I'm gonna ask you a simple question. So imagine, right, that you're trying to infer what is the preferred policy regarding, for instance, parental leave. So, you know, parental leave is an important public policy, right? It changes a lot of things, a lot of outcomes. So, for instance, you actually may improve the quality, you know, cognitive skills of your kid, but you also may affect the professional outcomes of the mother or the father. There is a trade-off for economists. There is always a trade-off, right? So having more time as parental leave have cost and also benefits, right? We're clear about that. Now, imagine you have a society, right, that offers different levels of parental leave, Canada being one, right? So let's focus on fathers, right, which is a new policy. So we're still deciding. So imagine that fathers, you know, should have 3 months, 6 months, a year of parental leave. There are 3 alternatives, right? 3 months parental leave, 6 months parental leave, 1 year parental leave. Which one is better? How do you find out? So I hire you as a consultant, right? And then you tell me, how should I find out which one is preferred by the citizens? So ideas?
Do you observe what happens? So,
Yeah, separate. That's a great question, right? Real preferences, right? So for instance, one thing would be, let's run an experiment, right? Let's give these 3 options to different people, right? Maybe there's variation in provinces, right? And then let's see what people do. Obviously, you know, one obvious choice is allowing them to have the 3 alternatives, right? So 3, 6, and 9. And then you see what they choose. So Severin is being like Samuelson, right? So he's saying, let's see what they do. So let's run a pilot and let's see what they do. So that's the economist's answer. But what is the usual answer, right? You're economist, obviously you're biased, but what would, you know, the average policymaker do? Run a survey, right?
A survey, right, yeah.
Yeah, you run a survey. But then Severin, can you tell me what would be the issues of running a survey? So if I run a survey asking them, hypothetically, what would you do? What would be the issues you think?
they probably want 12 months if they're going to get paid regardless. They just want as much time as they can get, and you won't get a proper sampling of what happens for the other consequences depending what alternatives people take.
Yeah, that's a great answer. There is also something called social desirability, right? For instance, what is what people want to hear, right? So you go, someone is interviewing you, right? And he's asking you, what do you want? So 3, 6, or 12. I say, well, you know, I really want to signal I care about my kids, right? And my kids are better, are more important than my job, right? So that's the social signaling. That's a situation. It's completely hypothetical, right? But that's something documented. It's called social desirability, right? You want to signal to people that you want to signal some value, right? That people will see in you. Okay, so the issue, right, is if you ask them, people will say, yeah, we want the 12 months, right? For sure, my kids are super important and whatever. Now, the real life, right, is that, for instance, in Canada, there is a huge issue that parents, male parents, are not taking the leave, right? So they have the option to take it, they take a reduced one, or they don't take it, okay? So there is a paper about that. One of our students did a job market paper about it, right? So then obviously they didn't want the 12 months, right? They wanted something smaller, right? Why? Because there's a cost, right? And maybe they care a little bit more about their jobs that they want to tell you, okay? So that's the difference between stated preferences, right? A survey versus revealed preferences, right? It sounds easy, right? For economists, because we're all economists here. But, you know, this is actually an insight from Samuels. He says, and he's a bit extreme, of course. He says, I don't believe anything you say. I will only believe what you choose. Okay, this is what Samuelson says. So, okay, great. So we're gonna define it. Okay. So reveal preference relation. We say A is directly reveal preferred to B, and we denoted with this symbol, but now with a superscript B, basically for direct revelation, right? Whenever A is chosen and the second alternative B is in the menu, right? Remember, and this is important, and this is a source of confusion, that at this stage, I'm not telling you that B is not chosen, right? I'm just telling you that B is available to you, but A is chosen. And this becomes hairy because of the choice correspondence business, right? We know that the choice correspondence can have more than one item chosen, right? But so this revelation, as you can imagine, is weak revelation. It includes a strict revelation and the weak indifference revelation, right? So at this stage, the fact that you chose A when B is available to you just means weak revelation. And of course, we omit the weak adjective and we say A is directly revealed preferred to B, okay? And the key word is directly and reveal. So important thing, this is not a model. So the symbol is tricky, and this is at least it was my main barrier to understand this chapter when I read Mas-Colel back in the time. So Mas-Colel uses this ugly notation, right? That basically is very similar between the symbol with the superscript D and the symbol without the D. These objects are very different. Of course, they are connected, but they are very different. Without the D, you know, this is basically a model of behavior, so a complete and transitive binary relation. This is basically a model. This doesn't have to do with data. This is an abstraction, a model, a creation of the mind. This thing instead, with a superscript D, is instead data, right? This is just a way to record the event that A is chosen, right, when B is affordable to you. So this is exactly what Severin says. I run a pilot. I run an experiment. I offer Ontarians 3 months leave, 6 months leave, and 12 months leave. And then I let them choose, right? If they chose the 6-month leave when the 12 months leave was available, they have revealed to me directly that they prefer A to B. Understood? Nothing fancy, right? It's just be careful with the symbols. Any questions here? Okay. And then basically we can make it strict and we say A is directly and strictly preferred to B. And we write it with a strict part of the symbol with a superscript D. Whenever A and B are in the menu, A is chosen, but B is not chosen. You see the difference, right? So in this part, I'm forcing also that B is not chosen, okay? So this is now a strict preference relation. And we say, and this is important, and again, the symbols in Masscolero are ugly, but they say basically A is indirectly, which we usually omit, and that's why it's in parentheses, reveal preferred to B whenever basically there is a sequence of alternatives, A1, A2, ... an, such that A1 is directly preferred to A1. Sorry, A is directly preferred to A1. A1 is directly preferred to A2, ... An is directly preferred to B, closing the chain such that A, you can infer, is better to B indirectly. Okay, so, and this is basically going back to Severin's point. So imagine I'm not able to run all possible menus as an experimenter, right? So I give to Ontarians 6 versus 12 months. Then I go to Quebec and I say, I offer you 3 versus 12 months, right? So then, you know, but I want to compare the ones that are never compared. So basically, you have 1 versus 2, right? And 2 versus 3. I want to compare 1 versus 3. So if I observe that 6 months is chosen over 12, right? And then basically 12 over 3, then I can infer that 6 is better than 3, for instance. You see? So basically, this is indirect revelation. Do you agree? So basically, this takes a second step, and then it interpolates from direct revelation, indirect revelation. Okay? All of these are definitions. Now, you tell me, do you think the indirect revelation makes sense? I think direct revelation is a little bit more defensible. Samuelson, you know, he was smart. I think is a nice idea. But do you think we can infer indirectly preferences in this way? Basically, I never compare directly A and B. I only compare, you know, indirectly A with other items. And then there is such a chain that you end up inferring that A is better than B by interpolation. What do you think about this, guys?
I think it's true if if they are rational, then it should be true. But they have to be rational.
That's a great point, Ahmad. Exactly right. So if you believe these guys are truly rational, you know, this way of inferring preference makes complete sense, right? But what about if they are not, right? So then we have to think harder. That's a great point, Ahmad. Yes. So under the assumption that people are behaving rationally, this is a good inference, okay? Else, you know, you have to be careful, right? Okay. So we have established reveal preference. These are just definitions. I haven't proven anything there. They are just definitions. And now we're gonna do something which is, you know, Samuelson invention. And then basically he's saying, look, we're gonna just impose a restriction on behavior, right? That has to do with reveal preferences, right? So I'm just gonna say, look, if I have a data set that satisfies this axiom, right? I'm gonna call this axiom the weak axiom reveal preference. I'm gonna call this data set consistent, right? And then I'm gonna try to link this consistency notion basically with testing of rationality. So in other words, what we're going to want to do now is to link the model of utility maximization with behavior. And what is behavior is choice correspondence, right? And how we're going to link it through reveal preference relations, okay? So the next step that we want to take is what Ahmad was already guessing, is that we want to go from data to the model and back and forth, right? So we want to go from data to the utility model maximization, okay? The model of utility maximization. How we're gonna do it? We're gonna do it with testable implications of utility maximization. I'm gonna introduce the first property that is gonna become the first testable implication of utility maximization, and this is called the weak axiom of reveal preference, right? And I'm gonna tell you in the two ways that it was presented. Historically, the first way it was introduced by Samuelson was with the following sentence. If for some menu, in the collection of menus. With X and Y in the menu, I observe that X is chosen out of the menu capital B. Then for any other menu B prime in the collection of menus, such that also X and Y are there, okay? But there may be other things in the B prime. And I also observe that Y is chosen from the second menu. Then you must have that X belongs to the choice from the second menu. So this is like a tongue twister. I don't know about you, but the first time I read it, for me was hard, right? So the way I understand it better is by using reveal preference relation. So again, what I'm gonna do now is I'm gonna define work using the reveal preference relations, and it's equivalent to the previous one. So work, in the nicer, more modern way to describe it, is the following. If X is directly referred to Y, then Y cannot be strictly referred to X. In symbols, if X is, as you can see with this symbol superscript dy, then not Y strict direct preference relation, reveal preference relation to X. Both definitions, definition 27 and definition 25, are exactly the same, okay? Just that the definition 27 is the modern way, okay? So for some good reason, right? I don't know about your brains. People understand things in different ways. You may like more definition 25. This was the original definition by Samuelson, right? But the newer definition, I think, is more telling. And what this is just saying is basically that work requires the data set, the behavior of the consumer to be such that if this consumer through choices reveals to me that X is better for him or her than Y, then it must be that Y is never revealed preferred, strictly better than X, okay? So in other words, Samuelson was thinking of a condition that you can call it no flipping preferences, right? So this person will never flip preferences. So again, Sebren, so imagine you run your pilot with these parental leave options, right? And then basically you don't want to observe citizens or subjects that will pick 6 months over 12 months, right? And then suddenly in a second pilot that you run, they switch to 12 better than 6, right? So and then in the second experiment, you allow them to have also the item with 3 months. So basically you can imagine an experiment that happens in 2 instances. So I'm describing, let's do a counterexample of warp. And before going, I realized we need a counterexample of warp. So counterexample, right? So let's imagine this Ontario, these leave situations, right? You have the parental leave of 3 months, parental leave of 6 months, parental leave of 12 months, right? Okay, this is my menu X. And then I have choice correspondence from P1, P3, sorry, P6, P12. This is the first experiment I ran. Everyone chooses P6, okay? Then I observe, I ask them again, but now I'm allowing them to have P3, P6, P12, right? And remember, this is a violation of warp, right? Here, these guys chose P6, right? Now they are gonna choose P12. This violates warp. Can you tell me why it violates warp, guys? Who can tell me?
Because because when they were presented with the same menu, they made different choices, and in one instance, it showed, as if I had mentioned earlier, they were indifferent between P6 and P12, and in another one, it showed as if they are P12 is directly preferred to P6.
Yeah, exactly, right? So let's formally put this thing. And then now we have the violation, right? So first you have P6 weekly better than P12, right? But then you have that P12 is strictly better than P6, right? So violation. Okay, so counterexample of work. So right now, right, this is a property, and as a property, it can be satisfied or it can be failed, right? Now, I'm just presenting you with an example of a data set that fails. Now, the first result, we start with a preference relation that is rational, complete and transitive. And then you have a data set, and this choice correspondence defined on this data set is rationalizable with this preference relation. Then the choice correspondence or the data set satisfies work, okay? So this is telling me, right, that if you have a rational consumer maximizing a complete and transitive preference relation, then they will generate a data set that is calligraphic BC that will satisfy work. This means that this is a testable implication, right? So basically, if you fail work, you can never be generated. So this is a contrapositive, right? So given that if you're rational, then the corresponding choice the corresponding choice data satisfies work, then it also must mean that if you fail work, then you cannot be rationalizable. Do you understand? So basically, what is P? This is a logical construction. So you have rationality implies work, right? So by the contrapositive, it means that not work, not rationality. Do you understand? So that's what I'm saying right now. So basically, this provides a test of rationality. If you fail work, you fail rationality. Understood? So this is the basis of any scientific theory, right? So you generate testable implications. If a theory doesn't have testable implications, it's called non-testable, it's non-scientific, right? So this is in the version of science, a la Popper, so very classical one, right? So before postmodernism. So I don't care about postmodernism, right? And this is for other things that are not econ. So, okay, so here you basically have a model, a theory of behavior, and they have testable implications, okay? And we show that a testable implication is work. Okay, great, so let's prove it. So start from C, choice correspondence, and imagine it's rationalizable. We know by definition, it means that the data, C of A, is equal to the set of maximizers of the preference relation of this symbol, okay? Now, let's start with the definition 2026, right? And actually, today I'm gonna do a different proof, right? So the premise is about work, right? So imagine, right? So let A be chosen out of menu A, right? When B is in A. This means that A is preferred to B. Notice here that this is the preference relation that is rationalizing, right? So it's not the revealed preference relation. This is just by definition. So the fact that C is chosen when B is there, it means that this is the maximum, right? So it has to be that the alternative is picked is better than the second alternative. Do you agree? According to the preference relation that is generating this. Everyone understands this step? Okay, good. Now, assume towards contradiction that there is another menu, B, such that A and B are in B, and that we observe that B is chosen out of B, and A is not chosen out of B. Okay? So this is my assumption towards contradiction. This is a proof using the contradiction technique. So if this is the case, it means that, first of all, B is preferred to A, And also, right, A is not preferred. So here I have a symbol that is being A. Is basically not, it is not preferred to, not possible that A is better than B. Okay, so hence B by definition is better than B. Okay, so this is impossible, right? Because the preference relation is complete and transitive. And by the proposition before that I told you that you can prove it to practice. We know that the strict part is irreflexive, right? So in other words, if we conclude at the same time, right, that B is better than A, and so in this case, basically, I did it the other way, sorry. So you have that B is better than A. Yeah, and then we have the opposite, basically. So we have that B is strictly better than A, and A is better than B. This is a contradiction. It's a contradiction.
So it's a proof by contradiction. Yeah.
Yeah. So then, you know, this cannot happen, and basically the first part that this we conclude that if A is chosen, right? And I'm gonna copy this part. Then for any other menu, it cannot be that B is strictly preferred than A, right? And this part here is just the statement that A is really preferred to B. So this is work. Okay. So this other proof, again, was the proof using the previous definition. The second proof uses so this proof 1, and proof 2 uses the previous definition, right? Using definition 25. So you can use whatever you want. Today I proved it slightly different to also practice the new definition. And the proof number 2 is the original in Mas-Colel, right? But we can prove it also using the more modern definition. So everyone is convinced by the proof. Else, I'm going to skip proof 2. And the conclusion of this is that word is the testable implication of rationality. Okay? So that's great, right? Because finally we have something that we can map from a mathematical model to data. That's the final end of the theory, right? So you write down a theory and then you can go and test it on an experiment, right? And you can see whether people are rational. Okay, so now here I have another example, right? That violation of word. Because I did one right now, I'm going to skip this one. Use whichever you find more compelling. The important thing is that in this second example, as well as the previous one, this data set I generate cannot be rationalized by any preference relation. So the moment you fail the weak axiom of revealed preference, it is impossible that the data set is a product of a maximization of a preference relation that is completely constant, right? So it's enough. Important thing, you have a study econometrics or statistics, right? And then when you basically fail a test, right? You need to say with some confidence, right, that something is true or not. In this world, there is no statistical noise. So basically, from an experiment with two menus, you can already reject for sure that rationality is behind the behavior. You don't need anything else, you know, to do statistical testing, because in this setup, we're assuming things are measured perfectly, right? So there is no statistical noise. Okay, so this is an important caveat that we have to keep in mind. In real life, scientists have noisy data, right? So this data we're trying to gather here is assumed to be perfect data from consumers, okay? So what does it mean to have noisy data when dealing with choice data? So for instance, Severin and us, we're imagining this pilot for the parental leave, right? So what does it mean to have a noisy data in that setup? For instance, one issue, right? It might be that even if you run your setup and then you do your pilot, there is some error when encoding the information from the pilot, right? Someone in the IT department messed it up and they recorded wrong part of the answers, right? So a lot of data have issues, right? So misrecordings, measurement error. So that may damage your data, right? Now with human subject is harder, right? Because a little bit you have to think as scientists that we're trying to elicit choice and to basically measure what people like. You have to consider that you have to look for the analogous of the vacuum in physics. So what is the analogous of a frictionless situation, right? So imagine, for instance, you're choosing from an experiment, a laboratory Nikon. I don't know if you have been able to participate as subject of an econ or psychology experiment. Usually these experiments involves the students sitting on a computer with a keyboard and a mouse, right? And answering a set of questions. So imagining such subject, you know, really had a crazy party night before going to the experiment at 9 a.m. next day. So night before, they were partying all night long. Do you think the choices of such a subject will be kind of representative or the usual choices this subject would make? If, for instance, this person is super hungover or not? Do you understand that?
Probably not.
Exactly, right? So imagine, for instance, this subject is super confused because they have a headache, right? Migraine. Those things are horrible. So you want to go through the experiment, you sit down, but you're fuzzy. Is it really representative of the usual behavior? This person may have a migraine once every month. So that's obviously a small fraction of the time this person's making choices, right? So yeah, you can see there with humans, it's very hard to have the vacuum, right? And you know, experimenters are really good in trying to, and this is an open question, by the way. So, but a lot of experimenters are really getting better into trying to get really nice in the vacuum choices from humans, right? But this is a little bit of a challenge we have. So here we're assuming in this setup, in this chapter, that the data we get is frictionless. So we get it from, you know, a perfect experimental situation. So hence, in this kind of setup, violations of the weak axiom are not attributed to measurement error or errors, you know, from these fuzzy lines, but rather to actual deviations from rationality. Do you understand that this is a limitation in real life, right? If you want to actually run a test of rationality in real life, you will have to deal with measurement error. Do you agree? But here, you know, we're going to assume this is not an issue, and we're just going to focus on the pure test. Hence, you know, having a simple experiment such as two menus, and you observe this pattern of behavior, we're done. We can conclude that rationality has failed. Okay?
I got a question, non-trivial question. I can see, and we saw it in the, for example, in the homework for the micro refresher this summer, that so if warp is violated, then we don't have rationalizability, but we can say also that preferences are not rational. I really don't get it.
Yeah, so
it's not the same.
It's not the same. So you're right. The language we have to be super careful, right? So preferences might be rational or not. For the purposes of this chapter, and actually most of the things we're going to study in the main class, we are going to always equate preferences with rational preferences, right? So in real life, in cutting edge research, people don't equate them, right? Because we can go deeper and beyond rationality. But right now, for this chapter and for Mascolet, basically preferences are almost synonymous of rational preferences. So what it means here, right? Basically, it means that yes, to being super precise about the answer to you, Martin, which is a great question, is that even if you fail warp, right, there may be some non-rational preferences that can generate this data, right? That's for sure. I haven't found the particular preference relation that is not complete and non-transitive, right? It has to fail one of them that generates this data. And then that's basically what decision theories do. So they take some very weird decision pattern that bias versus work and try to find a new model that will fit the data. But right now, the only thing we can say for sure is that there is no rational preference relation that can generate the data. So that's impossible, okay?
So we are actually rejecting rationality when warp does not hold.
Yeah, so when warp fails, rationality is out of the table. So it is failing completely, it cannot generate the data. It is basically very blunt. This test basically tells you exactly, you can never come from a rational agent. You fail warp, it is not from a rational agent.
So not only rationalizability, but also rationality. Okay.
Yep.
Okay. Got it.
Great. Okay, so again, remember that we have to be careful about the dataset structure because all of these choice correspondences are defined on the calligraphic B. Remember, this is a practicality, but it's actually very important. You can never have the whole power set, blah, blah, I told you already. So we are gonna restrict our notion of rationalizability also to the collection of menus, right? So for us, it's enough that we're able to rationalize the menus that we see, right? We're not gonna restrict that you rationalize things that we don't see, obviously. But you know, the fact that you have a preference relation will allow you to basically be able to predict out of sample. So, but that's another topic. So the topic of prediction is not for today. But remember that the only requirement is that you are rationalizable on the data. So this is an in-sample statement, okay? So only for the menus we see that are elements of the calligraphic B. Okay, with that caveat, let's go to our main proposition for today. And we're good on time. We have some 20 minutes to go. So if the data set with this collection of menus and the choice correspondence is such that one, warp is satisfied, and two, the collection of menus includes all subset of X up to 3 elements. So remember, this is the rich data set. So it has all double tones and all triple tones. So all pairwise comparisons and all triple tones. And next is also finite. So our choice set is limited to be a finite set. And we call this the rich data set. Then there is a rational preference relation, right? Complete and transitive that rationalizes the choice correspondence with respect to the collection of menus. Moreover, this is the only preference relation that does so. So it's also unique. So there was a question that Severin asked me in the summer. And he asked me basically, you know, the fact that you can conclude that there is a preference relation generating the data, and remember the quantifier, there exists a preference relation, right? It doesn't mean necessarily that such preference relation is the only one that can generate. So the fact that it's a unique preference relation, this is called identification problem, right? So here we're mixing the two. And first we have a testing characterization, what is called a characterization theorem, telling you that if you are rational, right, you satisfy warp. Not only that, basically, if warp is satisfied and the data set is rich, then also you can find a preference relation, right? So it goes both ways. This is called a characterization theorem. The previous one was just the testable implications. This is deeper because now it just tells you if warp is satisfied, now I can conclude, right, that there exists a preference relation that generates the data. So this is when the test passes, right? As opposed to just rejecting. And second, I'm also telling you something about identification. So if you recover such a preference that generates the data, this preference is going to be the only one that does so. I'm not telling you that there is only a unique utility. That's not the case, but there is a unique preference relation, okay? So I'm telling you a lot of information here. Again, to wit, there is a characterization theorem, which is a two-way street. It's telling you, if you're rational, warp holds. And the new thing, if warp holds, then I can construct a preference relation that generates the data, okay? So this is the other way street. This is the characterization theorem. And the final part, which is a kind of corollary, is the identification part that is telling you, remember the preference you constructed when warp was satisfied? Turns out this preference is unique, okay? It's the only one that can generate that data, okay? So a lot of information for sure. But remember, this is the first time we see this kind of theorem. It's called a characterization theorem, okay? So it tells you not only the testable implications, it also tells you that when the warp is satisfied, you can also construct a preference relation. So remember the question of Samuelson, how can we recover preferences, right? In the problem of the parental leave. If warp is satisfied, now we can also reconstruct the preference relation behind. We can identify the preference relation behind this behavior. Hence, knowing what people like, Not only that, the identification of what people like is unique. There is only one way they can rank alternatives. Do you understand? Okay, so in the last 5 minutes, I'm gonna prove it. And I'm gonna go slow, so if we don't finish, it's fine. But hopefully we finish. So remember, we already proved the testable implication part. So we know that if you're rational, then the choice set generated by a rational agent satisfies warp. We proved this already. So the only thing that remains to be proven is that what happens if you have a data set that satisfies the weak axiom of real preference? Can I construct a preference relation that generates the data? This is what I want to do, okay? This is what I want to do. So I want to build a model, right? So I'm gonna propose a preference relation that is gonna be equal to the revealed preference relation. And then I'm gonna show that in fact, this preference relation is complete and transitive, right? Because it has to be rational, so it has to be complete and transitive. I have to show that it's complete and transitive. And once I have shown that, I'm gonna show also that if this new preference relation I constructed that is complete and transitive can generate the data originally, okay? That's what I'm gonna do. So first, I propose the preference relation as equal to the revealed preference relation. Now, the revealed preference relation, as you remember, is defined as S is directly referred to Y whenever X is chosen and Y is present, okay? Now, first thing I do, check that the construct preference relation is complete. We want to check that either X is preferred to Y or Y is preferred to X for all X and Y. Because the data set is rich, we have that for any pair, first of all pairwise menus are included, right? So I have menus with 2 items, X and Y, conveniently. Now, this means that because the choice correspondence is non-empty, remember this assumption is non-empty, it has to be that X is chosen or Y is chosen, right? Do you agree with this statement? Because you're not empty out of X and Y, it has to be that choice correspondence contains X, contains Y, or contains X and Y at the same time. Do you agree? Because of non-emptiness, just as simple as that. So because of that, obviously, it has to be that X is referred to Y or Y is referred to X by definition. So this preference relation turns out to be complete. Important thing, what will happen if not every pairwise comparison is available? Imagine there is an item X and Z that is out of the experimental menus. So there is no comparison between X and Z. Can I conclude that the revealed preference relation is complete? No, right? Because this menu was missing I could never see from the choices how this person compare X and Z, right? So the comparison of X and Z was missing, okay? So the important thing about this proof is that the data set is rich, hence containing every pairwise comparison. The fact that you have every pairwise comparison and the non-emptiness of the choice correspondence implies that a revealed preference relation is complete, okay? If you remove the richness, it fails, okay? Got it? Now, let's go to transitivity. Now we're gonna use the tripletons, okay? So we have to prove basically that you have X better than Y and Y better than Z. Then it has to be, of course, that in the real preference relation, that X is preferred to Z. Now, by definition, we have that when X was picked from a menu where Y was present, and Y was picked from another menu when Z was present. Now, say we have a second menu, B double prime, such that X, Y, and Z belong to it. In particular, we can make it equal because we know we have all the tripletons. So the rich dataset assumption means that we have X, Y, and Z menus. Do you agree? So I'm assured to have the tripletons. Now we have the following cases. So I'm gonna do an exhaustive proof, case by case. First case, Z belongs to the choice set on the menu double prime. In this case, by the weak axiom, remember this is my premise, we have that Y belongs to the choice correspondence. Why? Remember that when Z was present, Y was chosen, right? So by warp, if Z belongs to the new menu, to the choice correspondence, then by warp, it must mean that Y also belongs to the choice correspondence, right? But now look at this. Because X is there, right? And I also already revealed to this experimenter that X is really preferred to Y, right? By warp again, it must mean that X also belongs to the choice correspondence, right? So this is a chain, right? It's like a combo. So once you have them, right, at the same time, this first case will reveal to me that X is indifferent to Y and indifferent to Z. So hence, I have verified in this case that the preference relation is transitive, right? Now, this is not the only case, right? So the second case. The other case is Z is not in the choice correspondence out of the menu X, Y, and Z. Because again, the choice set is not empty. By assumption, we know that either X belongs to the choice correspondence in the tripleton menu, in which case X is better than Z, and Z is transitive, right? Because just by construction, you can observe that it's transitive, or Y belongs to the choice from the tripleton, in which case by warp, X belongs to it, because I already revealed that X is preferred to Y, so warp implies that X is in this choice correspondence, and hence I conclude that X is indifferent to Y, and Y and X are better than Z, in which case it's also transitive, okay? So this proof only works because I have all tripletons, right? Remove one menu that has 3 items, X, Y, and Z, and then this doesn't work anymore. You need a rich data set, agree? And again, the non-emptiness, done? Now, final step of the proof. We're gonna show that the constructed choice revealed preference relation generates the data. So it is not enough that it's complete and transitive. It also has to be that when I maximize it, it has to generate the same data I'm observing, okay? So in particular, if I have something that is chosen out of menu B, this means that X is directly preferred to Y for all Y in B. But this also means, of course, that X belongs to the maximization of this preference relation, right? Automatically, this is by definition. Now, the part that is harder is that imagine I take a maximizer of the preference relation. So X is the maximum in the menu B prime, according to the construct preference relation. Now, this implies that X is better than Y for all Y in the second menu, B prime. This implies that there exists some menu BY for all Y in this B prime, such that X is chosen in this menu because it's not empty. And the warp implies that because it has to be that X is chosen there as well. then obviously, as you can see, this implies that these two menus are the same. So in other words, I have shown to you that the constructed preference relation, which is in fact the Samuelson revealed preference relation, when you apply it to tupletons and tripletons, so rich data sets, it gives you a complete and transitive relation. Not only that, when warp holds, of course, only if warp holds. Not only that, but also when I maximize this constructed preference relation, I generate the original data. Okay. Now, for uniqueness, and note that when you have the calligraphic D, which is rich, includes all pairs and all tripletons, basically it must mean that is the unique revelation of preference relation, because a preference relation is defined by all pairwise comparisons, right? So having basically all doubletons is enough to pin down exactly what people like. Okay, so this is it. I'm going to stop the recording now.